I'm talking very informally because the class has a few students you can interact all the time. I always ask them about something. Well, sometimes they answer me, but probably most of the topics are new for the students, but maybe they are motivated, or maybe they are motivated by my talk. Okay, now I'm going to give you some examples of applications for the new ICM model. I started this one yesterday. This is called the self-cascade MOSFET. It's one MOSFET on top of the other, and they share gate voltage, and they have this common node which is labeled Vx. And using the new ICM model, we can find this expression here, right? I told you that if this IF2 is much less than 1, this means weak inversion, then Vx over phi t tends to the natural log of alpha, where alpha is just a ratio. And this is a constant factor because it's a ratio of dimensions. S2 is the W over L of transistor 2. S1, the same definition for transistor 1. Okay? So if IF2 is small, or alpha IF2 is small, we have this value here, Vx over phi t. So this can be used as a thermal sensor, because this is a constant term which independs of it's not dependent of the temperature, and this one is the temperature, the absolute temperature, Kt over Q. Okay. So we have Vx proportional to the absolute temperature. So, but we have a different interpretation of this formula because we are able to build a circuit in which IF2 is what we call the generator of a specific current. If IF2 is not constant with temperature, it's independent of T, then this expression gives a term proportional to the temperature. This term is independent of temperature, so you have Vx proportional to phi t. So why am I explaining this? Because we have means to generate a current which is proportional to the specific current. And look here, what's IF2? IF2 is IF2 over IS2. This is ID2. Suppose that IR2 is negative, okay? So this is ID2 over IS2. If this term is proportional to this one, this IF2 is independent of T. Okay? Suppose that all this number is not a function of T, is a constant with temperature. Then we have a Vx which is this term times a constant term which is independent of temperature. So we are able to generate a specific current which is proportional to the specific current. Okay, that's the result. Sorry, this is the result of a publication with Conrado Rossi, my colleague, Gallup-Montoro. And we showed that the voltage, the experimental voltage that we obtained from this structure is, I would say, almost proportional to temperature. This would be the result in the case of an ideal self-cascade mirror. But we have a small offset compared to the ideal straight line. Okay? So this is one of the main subjects of our research. We use this block a lot of times for several types of circuits. So this block, the self-cascade mirror, is very useful for design. I can show you the next example. You have a lot of self-cascade MOSFETs here, right? One different self-cascade with three transistors in the connection. Two. But the self-cascade here is just this one, because this one doesn't share the gate voltage with this one. What's the purpose of this circuit? It's to generate a MOS-only voltage reference. Okay. What's the meaning of it? Let me explain how this circuit can generate a MOS-only voltage reference. We want a voltage reference, to be independent of temperature. Okay, so we need this graph, Vref versus temperature. Say from -20 to, depends on the application, up to 80 centigrades. This device here, M5, is such that the gate voltage is like this. It's a straight line, but which decreases with temperature, right? Now, these connections here, one connection, second, the third connection, they gave us, I will not derive the equation because there are lots of transistors here, but I have calculated the sizes of the transistors, the aspect ratio, this is W over L, in order to have some voltage, first one, the second one, all of them are that voltage, proportional to absolute temperature. And each voltage of this is on 1/3 of the total voltage. I have 3 equal voltages here, okay? So, and you see that from Kirchhoff's law that this voltage at the output equals this one plus this one plus this one plus this one. So the voltage at the output is V, I call V ref, is V, which I call Ctet. Ctet is complementary to absolute temperature. It decreases with temperature. Plus that one, 2, and Okay? Since the three voltages are the same at 1, 2, and 3, I calculated the voltage to be the same, right? I can simply write here that this is plus 3 E that. Okay? Okay, the calculations are not important. I just want to show you that you can build a reference voltage using MOSFET transistors. Okay, now if you have this pitet such that 3 pitet is exactly like this one, but the opposite slope. If you add these two curves, you have a constant one, right? So this is the basic principle that is used in the band gap references. The difference is that in the band gap reference, you use here a bipolar transistor instead of a MOS transistor. So this transistor N5 is replacing what should usually be a bipolar transistor. Okay, so this also works for MOSFET devices. Well, this is just an equation to show what would be the DVO dt 0. Ideally, I don't want this reference to change with temperature, so this should be valid for the whole temperature range. Usually you don't have this sum, but you have something like this. You have some variation around the nominal value. Okay? This is also typical of band gap references based on the bipolar transistor. Any question here? Have you already studied the band gap reference? No, not yet. Maybe. I don't know if you teach this subject here. There is a course on analog electronics, maybe.
Yes, but nowadays they didn't study band gap.
No, not maybe. Okay.
No, never even studied band gap.
What do you study? Operation differential amplifiers, current mirrors, operational amplifiers, cascode, frequency response,
No, frequency response, no. But,
switched capacitors,
yes,
switch capacitors,
no band gap reference.
no band gap. Okay, this is the, I suppose it's the second course about electronics, or how many courses do you have on analog electronics? You study first devices, diodes, transistors.
Yeah. The second is more like cascode,
differential mirrors, current mirrors,
feedback.
Mirrors.
Well, that's the second, and the third.
There is a third course on
about the filters, ADC stacks, and also
ADCs, DACs. Oh, it's a top level course. I would say you study blocks, not at the transistor level. Sometimes just blocks. A filter is an operation amplifier, resistors, capacitors, and so on.
But at the summer, we will have a course of analog integrated circuits.
Okay.
We will have.
I remember we have that long time ago. I don't remember with this Noza.
Analog ICs. Okay, let's move to another application. This is similar to the circuits. I would say not similar, but you have a bipolar transistor here, right? This bipolar transistor has the function of the MOSFET M5 that I showed before. It generates a CTAT dependence of V on the temperature. It's, I would say, the function is the same, okay? Now, this is a sub-band gap because you divide the VBE voltage by two junctions here. You have this junction and this one. So this VBE here is divided by two. So 1/2 of the VBE appears here. That's the reason why this circuit is called a sub-band gap. Because the original band gap adds this voltage to a that voltage, as I did before, without making this division by two. Okay? And after that, you have a lot of blocks here. And these blocks generate that voltage. The basic idea is exactly the same as I showed before. You have a CTAT voltage, then you generate that voltage, which added to the CTAT voltage gives rise to a constant voltage. Okay, the basic idea is the same, but this is a very interesting paper, and the author have very good results using this topology. So the basic here is that for a conventional band gap reference, you need at least 1.7, 1.8 volts of power supply. But in this case, maybe 1.1, 1.2. And many technologies nowadays cannot be supplied by more than, say, 1.3, 1.4 volts. This is very important for more recent technologies. So you have this division here, and you have a sub-band gap reference, which can be supplied by a voltage source of 1.2, 1.1 volts. Right. Okay. Now I'm going to show an application that uses two SCMs. So you have here SCM 1.2 and SCM 3.4. Well, 1.2 because it's associated with M1 and 2 and 3 and 4. So we have two SCMs. Now these SCMs are different. They must be different. I'm going to show why they must be different. And now I have two different curves. The first one, this blue one, is for this circuit here. This is a plot of Vx normalized to phi t versus Ix normalized to some factor here, which is the chip specific current. The normalization current is not important. So this is the curve, the voltage at this node for different values of Ix, okay? So I have a curve like this. It's kind of constant for very low inversion levels. This means weak inversion. And then it increases according to this curve. The second one, SCM 3.4, is represented by this characteristic, okay? So you have two different SCM, okay? And you know that they intercept at a certain point, okay? At this point, the currents are the same at the two transistors, and the voltages are the same, okay? So now, if you have a way to reach to this point, let's try it, okay? And how is the way? I'll show you a circuit in which you will have two equal currents and two equal voltages. And I'm going to using a simple operational amplifier to do this. Okay, let's assume that the operational amplifier is ideal. Okay, in fact, we will have to take into account the offset, the voltage gain of the op amp, but let's assume that the op amp is ideal. Okay, so let's move to the next circuit. Oh, here is the op amp. Okay. Here you have two PMOS devices, identical PMOS devices. Okay, so you have a one-to-one current mirror. The current through these two transistors is the same. So you have, as you need in the previous slide, two equal currents, right? And here you have a virtual short circuit. So this voltage equals this one. So what's the result? The result will be this one here. You have an Ix normalized, doesn't matter, equal to 10 to minus 1, and Vx equal to around 25. Okay? We have used this kind of current source. This is a current source. You generate a current source, which is a copy of the chip specific. This is very important because this is a transistor parameter. Okay, no, it's not an arbitrary parameter. We are seeing here a way to generate a current, which is say a replica of the chip specific current of the MOSFET, right? Of course, there are several ways, several geometries. Well, it depends on the current that you want, on the voltage that you want, but you have equations, you have a way to reach a current that's needed for your design. And after having, say, this current here, you can replicate it. Just include another transistor, and you can drive this current to another part of the circuit. Say, for example, to bias a differential amplifier. Okay? And so on. There are some tricks to generate this circuit. First, sometimes you need what we call a startup circuit. Oh, what's a startup circuit? You probably remember of those old cars of 1 century ago. There was a car, but the driver had to get out the vehicle and then put something and manivela. After that, oh, the engine has started up. Then I go to the car and I can drive my car. Okay, this you will see from several films of Charles Chaplin and others that there was the car of the beginning of the 20th century. And you need something similar here. I'm not going to show this a circuit for starting. Second problem is that you cannot exchange these two terminals because you have both types of feedback here. You have negative feedback. Okay, negative feedback is from here. This is a plus sign, but this is an inverter. So, and the positive feedback is from here. Okay, and you have to take care of the feedback because otherwise the circuit will be unstable and it will not reach the operating point that you are looking for. Okay. Well, this is one of the most important applications of the assembly. In general, we don't use this operation amplifier here. We use a mosfet circuit, which is called voltage following, current mirror. It's a combination of 4 or 6 transistors, but I would say that the function, the purpose of this block is similar to that of the operation. Okay, we have several publications around this type of circuit, which is really, really important and really, really useful. Okay? Okay. So far, I have talked about the 3 p.m. model, 3 parameters. Threshold voltage, specific current, and slope factor. Now, I'm including the 4th parameter, which is called the drain-induced barrier lowering. Why is this parameter important? Because we don't have a saturation in the transistor. We have to model the so-called short channel effects. And up to now, I have talked about the long channel device. Now let's talk about the short channel effects. Well, what's the reason for this parameter? When you increase the drain source voltage, you modify the voltage profile along the channel. So you have to include this to calculate the threshold voltage. The threshold voltage is affected by both the source voltage and the drain voltage. So you have to include this. And this parameter is called sigma, and it's simply called as a VIBL factor. Okay? So from now on, we should be careful and apply this VT when we calculate the UCCM or the UICM. But in most of the cases, we assume that this difference or this factor is small. Look at here. The sigma, this is a plot of sigma in terms of the temperature. It doesn't vary too much, say 20% from the lowest to the highest value. But there's another problem with this parameter. It's also a function of VDB and VSB. It's not a constant factor. This should be here. Sigma is a function of VSB and VDB, and this term sigma is multiplied by both VSB and VDB. So, but for first order calculations, and in general, or in most cases, you are not interested about accuracy, you can use this sigma as a constant. Say, in this case, 25, 26 millivolts per volt. What's the meaning of this? Oh, if VSB or VDB changes 1 volt, the VT will change, say, 25 millivolts around the nominal value. So instead of, let's say, the VT 0 is 500 millivolts, okay? This VT affected by VDB, for example, would be 500 millivolts minus 25 millivolts in the example that I talked about. I spoke before. Okay? So, but you should take care of this because this is very important to calculate the slope of the characteristic in saturation. Okay? In the long channel model, the transistor current saturates. When you use sigma, you have a slope which is not 0. Okay, let me talk about technology right now. When we talk about the technology, we want to know, well, what's the spreading of the technology? We have nominal values of VT, for example, mobility, slope factor, but all these parameters, they change. If you send your chip to run today, it will have a different characteristic if you send it tomorrow or the other day. It's like, well, the process has some variations. It's like taking a resistor from the drawer. The nominal value is 10 kiloohms, but we measure 9.85, 9.7, 10.02, etc., etc. So even if you have the resistor from the same lot, they can change a bit. So the manufacturer gives you information about this variation, because you have to be sure that your design will work correctly for the nominal values or for, say, the limit values of the technology. Okay, so this is an example. In the CMOS technology, the main components are the NMOS device and the PMOS device, NMOS transistor, PMOS transistor. For this technology, we extracted the parameters for a transistor which has a width of 1 micrometer and a length of 1 micrometer. Okay, these are the nominal values that were simulated. Okay, for the NMOS transistor, VT is 291 and PMOS minus 211. And you have the values of IS, and you see that there is a spreading from here to here. This is what they call the slow parameters. What means slow? If you use this transistor here and this one, your circuit will be slower. And if you use those on the right, they will be faster. Like a resistor, 9.1 with respect to 10 is faster because, say, a time constant is RC. So if R is smaller, RC is smaller, time constant is smaller. It's very similar. Okay. The specific current of this transistor, you see here, the nominal values. You see that for the NMOS device, you have almost a factor of 3 higher than for the PMOS device. Differences due to the mobilities. Okay. And so on. The factor N is almost insensitive to fast or slow. Sigma is also almost insensitive to the spreading of the current. Okay. You have another table here, which is for another transistor. Yes. No, the size is different. It's different here. You see, L is 0.3. So you have some differences between the parameters, right?
¿El parámetro que está cambiando es la longitud hacia menos siempre o puede ser desproporcional? Porque en el primero es 1 a 1.
1 a 1, yes. When in integrated circuits, you change the length. You change the length. So let's say a technology 130 nanometers. This is the minimum channel length, but you can have twice this length 3 times, 1.5 times. You don't have all degrees of freedom. You also have a higher limit, say, I don't know, because why the manufacturers give a higher limit? Because they don't characterize for very, say, long transistors. So the parameters that they give to you are according to certain dimensions, width and length. So they have a set of parameters depending on the width, depending on the length, okay? They call this binning. It's like putting something here and here. But of course, this is very important because the parameters depend on the sizes. Of course, they don't vary too much, but you see here, let's take this one here. Oh, you see a huge difference here for the IS. Oh, but this is natural because you have a factor of 3 in the S parameter. Aspect ratio, recall that the drain current is proportional to W over L. It's like in the resistance. It's the same. Yes, if the width is higher, you have more conductance. Current is higher. Okay. If L decreases the conductance, increases the resistance, the channel length or the resistor length, they decrease the current, right?
¿Y hay un compromiso con respecto a la distancia entre un MOSFET y otro MOSFET?
Yes. There is a lot of rules. You have rules for printed circuit. Or
Claro.
you cannot say 2 metal lines. They cannot be very close. Otherwise, when you put some chemical inside to remove the copper, maybe there is some point here that the copper field makes like this and will touch the next line. So you have to ensure that the lines will not go together. There will not be a short circuit. And the lines cannot be very thin because they can open. So you have lots of rules, more than 200. But you don't check this personally because if you have a circuit with 1 million transistors, you cannot do this. You have EDA tools, electronic design automation tools, who do this for you. If you violate some rule, they tell, oh, you have a problem here. And the software, the EDA tool will indicate, well, where is the problem? What should I do? Then, you have not respected the distance rule, so increase the distance. So you have lots of rules, and you don't have to know all of them by heart, but you have programs that will help you during the design of your circuits. Okay. It's a world of rules and schematics, and you have design tools, but usually they are very, very expensive. Some groups pay $1 million per year or something. We have almost for free these EDA tools because we are academic institution. So the value that we pay for year is about around $5,000. It is nothing for the who give the software. In fact, they are giving the software. But of course, they are interested in the academic institutions because these engineers will be future designers and will buy their tools. Okay, but it's a very rich area, I would say. Okay, here are some examples of simulation using PSIM. PSIM is the industrial standard, and ACM. Of course, I'm fooling you because this is the log scale. So you don't see any difference, right? But in fact, there is a small difference between the two curves. You see here, maybe 20% or something. This is for these curves are for the long channel Any MOS, I don't, what's one channel here? Oh, no, we didn't say, sorry. Maybe 10 micrometers, the channel of channel length. Here for the long channel PMOS, and for the short channel in MOS, and for the short channel PMOS. The message here is the following. Oh, you have BSIM, which is the industrial industrial model of the transistor, which has lots of parameters. Why don't we use a more simplified model? And the ACM model is much more simplified than the BSIM model. It gives almost the same results as the BSIM model. Okay, at least for these are DC characteristics, direct current, not AC currents. Okay. Another set of curves. In here you have the variation of the drain current in terms of the drain to source voltage. You see that this is more difficult to follow, but you have a small difference in the absolute value, and you have a small difference in slope as well. Okay. I'd say that the most important characteristic here, or it's really important, is the slope of the curve. This is for the long channel device. For the short channel device, you have a huge difference here, not in the absolute values, but in the slope. Okay. Okay, these curves are for the base of the MOS inverter. I suppose that you are familiar with. Okay. I suppose you know what these curves mean. These are voltage transfer curves. It's the output voltage in terms of the input voltage. I know when the input is low, this transistor is cut off, and this is on. So you connect this node here. When you have high voltage at the input, this transistor is on, this is off. This is the most simple interpretation of this bond. But what happens when you sweep V in from 0 to say VDD? Let's start with this one. And this set of curves is for VDD equal to 300 millivolts. We love low voltage. We have worked a lot on low voltage circuits. Circuits that are able to operate from 5 millivolts. Have you heard of it? Oh. We worked on oscillators that start from 3.5 millivolts. Using integrated circuits or integrated transistors, but off-the-shelf inductors. Because inductors in integrated circuits are very, I would say, poor. They have a very low quality factor. You know that an ideal inductor has a quality factor, say, infinite. It doesn't have losses. Okay, but this is very difficult to obtain. Typical inductors of off-the-shelf inductors have a Q around 100, 150. But inductors in integrated technology have a Q maximum around 8 or 10.
This is too poor.
Yes, they are really lossy.
Yeah.
They waste a lot of energy. So it's difficult to have an oscillator using low Q inductors. Okay. Now, so we used off-the-shelf inductors to generate oscillations from 3.5 millivolts or 4 millivolts of supply voltage. VDD around 4 millivolts. Okay. In the case of the inductor, we are showing here an inductor supplied by 300 millivolts. And here are the curves obtained using BSIM, the dashed curves, and the 4 PM model of the transistor. Okay, and the curves are very, very close to each other. No. Okay, this is for the typical case for the nominal values of the parameters. Here for the fast for N is low for P. And here is slow for N and fast for P. So you have, when you design a circuit, even a digital circuit, you have to take care of this because you can have some fluctuation. Oh, you generally design your circuit based on these characteristics, typical, such as an RC circuit. You buy the components, you build your circuit. Oh, the nominal value is 10 kilo ohms and 1 microfarad, but you have variations around the nominal values. So you have to live with this. For this case, the supply voltage is 100 millivolts. And see how the performance of the transfer curve degrades when the technology changes. Look here. In this case, if you have, for example, 0 volts, you have the output is not VDD. Oh, it's close to VDD, but it's not VDD. Okay, it has been demonstrated that in CMOS technology, at room temperature, the minimum supply voltage is 36 millivolts. There's a famous paper by Professor Mendel. Professor Mendel passed away maybe 2 years ago. But he left this wonderful paper about the CMOS digital circuits. What's valid for the inverter is also valid for combinational circuits, for RAMs, and a lot of components, a lot of structures. Okay, and we have studied this component under very, very low supply voltage. One of our main topics of research. Oh, this is a very simple circuit, which is called an amplifier. Okay, in this example, I assume that there is an ideal current source here, which is the drain current of the transistor. Okay, and let's assume that this circuit operates in open circuit as shown here, but in fact, you cannot operate this circuit, the circuit shown here, with the circuit open. Okay, but assuming that this is just a hypothetical assumption for our interpretation of the meaning of the ACM model applied to this circuit. I suppose that you know how to calculate the frequency response of the circuit once you have the AC model of the transistor. Okay, What's the AC model? Well, an input capacitance, a coupling capacitance between this node and this one. A current controlled, a voltage controlled current source, and an output resistance and an output capacitance. Okay. I'm going to interpret this circuit. Suppose that I have this circuit and I need a unit gain frequency. Okay, the unit gain frequency of this circuit is GM over CL. What's GM? GM is these parameters. It's the gate transconductance. It represents how the gate voltage is converted into a current. Okay. Just to, I'm anticipating this value here. This will be given tomorrow. What's the GM of the transistor? Doesn't matter right now. It's just an example to show the power of having a good model for the MOSFET. Okay. So GM is given by this factor. So if you assume that you need a given unit gain frequency for this amplifier, okay, and assume that you know the load capacitance, what should be the GM? Well, GM should be omega U times CL. That's it. So GM must be a constant, right? It's like in a bipolar design. So you need a constant GM, which is the product of omega U times CL. Then, so I have degrees of freedom to choose this GM. I have this IS and I have the IB. What's IS? IS, it's the specific current. Well, this is a technology factor. I cannot change it. It's almost constant. But I can change this here, W and F. In our example, I'm going to assume that L is a constant. I cannot change it. For some reason, I cannot change the channel length. Then that's the variable that I can choose, W. That's the design parameter. And the other parameter is the bias current. Okay? Then I have two parameters to choose, bias current and IS. One or the other. Once I have fixed one, the other is automatically calculated to give a constant GM. The GM should be constant. So let's move to. Then I made some calculations using a given model, the ACM model, and I found out that this graph represents transistor aspect ratio versus what I call excess current. Okay. There's one message here. There is a minimum current that satisfies this design. There is a minimum. And this minimum is given in weak inversion. And the weak inversion, you know this from bipolars. Do you remember this? The transconductance of the bipolar, which is the dependence of the collector current on VB, is IC over phi t. Okay. In the case of the MOSFET, you have almost the same. This would be ID, which it's called IB in this example. IB equals ID. And there is another factor here, which is N. But it's almost like in the bipolar. The difference from the MOSFET to the bipolar, okay, is that you have this N here, which is close to 1, but is more than 1. So this would be the minimum current, which I call minimum or EWB with inversion is GM times N phi T. So now I have a plot of W over L in terms of a normalization factor. It doesn't matter what it is. Assume that L is constant. So the gate area, which means silicon area, okay, is W times L. So if L is kept constant, well, the gate area is proportional to W. That's it. So I would read this axis here as silicon area or transistor area. Let's put it for a simple design. And this axis is the current excess or the relative current excess relative to the minimum that I have. So from this graph, you see that if you use less current, you need more area. If you use more W, you can use more current. Or less W, sorry, less W means more current. Okay, so typically in a project, in a design, you exchange area and current. For accurate designs in general, you must spend both current and area. This is a law. You don't run away from it because in general, I'm not talking about an important parameter of MOSFETs, which is matching. Matching is especially for advanced technology. Matching is one of the most important parameters. What's matching? Well, you know the differential amplifier. For the differential amplifier, you need two identical transistors at the input. If they don't match, you have what we call offsets. Okay? And the offset is proportional to the inverse of the area. The higher the area, the lower the offset. Okay? And in some cases, you have to deal with the current. Because if you increase the area, you have to feed all the transistors. How do you increase the area? You can put a lot of transistors in parallel, for example, instead of increasing W. This is one important approach that we use when designing a circuit. Instead of increasing the area, you put a lot of transistors in parallel, for example. Sometimes you put them in series. Okay? So, area is a need when precision is required. Area, you spend in general silicon area. Okay, but in this case here, I'm not showing the matching problem. I'm just showing simple transistor, a simple amplifier, which contains just one transistor and one current source. Okay. Okay, let's move to the fifth parameter. The fifth parameter is associated with what we call the velocity saturation phenomenon. What's this? Well, when I derived the drain equation of the transistor, I assume that the relationship between velocity and field, I call electric field, is given by the mobility. Okay, velocity is proportional to the field through this constant, which is called mobility. Mobility is the, I would say, the inverse of viscosity in a liquid. Okay, if you have a liquid with a high viscosity, it means that when you put some object inside the liquid, it will take a lot of time to move, right? Mobility is the inverse of the, okay? And I assume that mobility is a constant factor independent of the electric field. In practice, this is not true. For the silicon, you have something like this. Okay? I have assumed so far that the model of the mobility followed a straight line. No, this is not true. You have a nonlinear dependence of the velocity on the electric field. And the dependence is something like this, and there is what we call the saturation velocity. What's the saturation velocity? It's around 10 to the 7 centimeters per second. If you compare this with light velocity in vacuum, 300,000 kilometers per second. This is times 3 centimeters per second. I don't know if I'm right. So, the saturation velocity in silicon is 3,000 less than the light velocity. You have a factor of 3,000 from here to here. Why such a low limit? Because the electrons and the holes don't move without collisions. They are always submitted to interaction with the silicon crystal. So they have what we call the Brownian motion. So the Brownian motion is a phenomenon which limits this velocity to saturation velocity. So you have something like this, which is modeled with this formula. Okay? So this is a simple formula. And this parameter, which is called the critical field, is the relationship between this set and US. I say, is this very accurate? Doesn't matter, but it's an approximation. And this approximation gives us a way to reach to a simplified model, including this phenomenon. Okay? So this is the reason why we are using this very simple formula to include in our model. Okay, so you have some algebra now. And with this model, we have modified the ACM model and to include this fifth parameter, sorry. And this equation is the equation that relates drain current with charge densities as source and drain. Now, let's include the effect of the saturation velocity. Look here, you have this inclusion in the denominator of the same function. So this is very elegant, okay? You don't modify the basic structure of the 3PM model. You just include this term here, and you see that if QS equals QD, the formula is the same as before. Okay? What's the meaning of QS equal to QD? It's the channel is uniform. You don't have a current. So you don't have a field. The field, the longitude of field is 0. So this is the beginning of the characteristic. Okay? And now you have, it's very easy to handle this result. And this parameter here, which is called the zeta parameter, the letter zeta, characterizes a ratio of diffusion related velocity, which is this term. This is related to diffusion. This term here is the diffusion constant given by Einstein relationship, U times phi p divided by L. This is then a velocity normalized to the saturation velocity. Okay. So the inclusion of this term is important for, I would say, for high frequency or high current devices, not for low current devices, because this phenomenon occurs just for very high currents or very high current densities. Typically, this parameter is very important for RF or very high frequency circuits. Okay. This picture here shows a profile of the inversion charge density from source to drain. Okay, let's assume here that the source voltage is constant, the gate voltage, the only voltage that changes is the drain voltage. In the first curve, this one here, VDS equals 0. This means that the channel is uniform. Oh, okay. Then I'm increasing the drain to source voltage. Source is fixed, drain changes a bit. The inversion charge density at this node becomes to decrease. But it cannot decrease indefinitely. It must keep a certain amount of charge. Otherwise, well, you don't have the current. Okay? It's like in a pipe. So assuming that first case, VDS equal to 0, you have a pipe which is uniform from source to drain. Now you increase the drain voltage. The pipe becomes thinner at the drain side. Here it's still the opposite, thick. It's still thick. So you have a cone section. So you decrease or you increase the drain voltage, the diameter of the drain reduce, but it cannot reduce indefinitely. Otherwise, you don't have molecules to pass through this side of the. So this is a very good analogy. If you have to keep a current and you have a maximum velocity of molecules, assume this is water, okay, you have to keep a minimum channel diameter at this side. Okay, so this is an important parameter, of course. And here I call this minimum charge at the drain side as Q prime ID set. Okay, so the model for including this phenomenon should include this term here, this one here. And finally, we have something like this, and we can calculate this QT saturation, which is equivalent to this minimum diameter of the pipe at the drain side. Okay, but in terms of charge, I could say that I could calculate this in terms of molecules at the drain side as well. Okay, I need some minimum amount of molecules that keep that current. Right? So this is the formulation, but don't worry about this. We will not use this anymore. This is useful for high frequency circuits, and I'm talking only about low frequency circuits. Okay, but now this equation is what we have so far written. This for the source side, and you have this picture here. You are increasing the voltage, the drain voltage, right? So, but for the source, you don't see any change in the basic equation. But for the drain, you should modify the equation. This is derived from the UCCM. Now you have to modify to include this effect into account. Okay? This is would be the calculation for the inversion charge density as the source, and this would be for the inversion charge density at the drain. Look, this parameter which is written here is a function of QS. So using a previous formula here, okay, if I know QS, okay, I can go to that formula, then replace that value here, and my incognita, my variable to be determined is the QD, the drain charge density. Okay. But let's move for some examples. And now this effect is important because you can see here, you have some simulation curves here in terms of the gate to bulk voltage. And you see that for high gate to bulk voltage, when the current increases a lot, you have a huge difference between these blue lines, and which is 4 pm, which do not include the effect of the saturation velocity. But when you include this fifth parameter, you have a good fitting of the BC. Okay, this is in the linear scale here. The linear scale has a huge difference. You see, almost a factor of 2 or 3 with respect to BC. When you include this fifth parameter, the curves match very closely. Okay? You have another example here. This is for a different technology. It's not CMOS or a different simulator. It's a silicon on insulator. I suppose that you have heard of this technology. But the model also fits the SOI simulation. This is a comparison of our model with our model, but in this case, we have this is the 3-parameter model. You have a full saturation. Okay, this is the long channel model. And when you include the short channel parameters, the DIBL and the velocity saturation, you have this behavior here. Okay? And you see that for high currents, you have a huge difference. This will be closer to the real case. I don't have this. No, this is not a long channel because this is a CMOS, 0.18 CMOS technology. This is the minimum channel, minimum channel for this technology. Okay? I would say it's a wide transistor because this number is much higher than the minimum width. In this technology, the minimum width is around 0.22 or 220 nanometers. So this is around 20 times wider than the minimum channel width.
It's low, this place is too high.
Wow, the slope?
The
Yeah.
slope, yeah.
But this happens in weak inversion because in weak inversion you have an exponential dependence not in change. Let me put this here, and VT now is a function of sigma. Okay, sigma VDV. VD is changing. So VT is changing, and it's an exponential change now. But here in this region is not longer exponential.
No.
It's kind of a linear or parabolic, something like this. You see that the transistor is much more affected by VT in weak inversion than in strong inversion, because in the weak inversion region, subthreshold, the VT affects exponentially the drain current, while in the strong inversion region, the effect is parabolic, and it's subtracted from VG. The higher the VG, the less the effect of VT. The sensitivity to VT decreases with the increasing current. Okay?
Yeah, in the strong conversion, they have a light really slow.
You will see it's a very small slope, but in weak inversion, it's a huge slope. Okay? This is another example of the application of the five parameter model. In this case, you have several inverter transfer characteristics. This is V out versus V in for an inverter, the CMOS inverter. Here, this first one is for 400 millivolts. You see that the logic levels are very clear here, 400 millivolts and 0. But for 100 millivolts, well, I would say the high and low levels are very clearly defined. But for 60 millivolts of supply voltage, they are not very clear. They are not exactly 60 millivolt and 0 millivolt. Okay? And this is a curve for typical values. If you change one of the transistor, this curve will move from to the left or to the right, depending on the transistor, which is, let's say, stronger. This is the current gain. What's the current gain? The current gain is dV out, derivative of the output relative to the input. Okay? So the derivative of this curve, for example, is higher at this point. It's almost 0 here and almost here, 0 here as well. Okay? So you have a set of gains. Why I'm showing this? This device, the digital inverter, is also used as analog amplifier. Look here. This component has a very high slope here. This is very useful for inverting amplifiers. Okay? This is one of the most used topologies for inverting amplifiers, the CMOS inverter. Finally, this last set of curves here represents the short circuit current. What's the short circuit current? Assume that you have a very, very slow input voltage here, which changes from 0 to VDD. Then you have some current crossing from VDD to ground, right? This is not an ideal circuit. Even when the voltage here is 0, this transistor has some leakage. I say, if VGS is 0, the current is 0? No, the current is not 0. You have some current. If VGS increases, this voltage increases, you have some increase in the current. And here, when both transistors are in this point here, in the middle of the curve, you have the peak of the current, which goes from VDD to 0. Yes. Say, for example, here at 200 millivolts, the value of VDD is 400 millivolts, so the current reaches a peak of approximately 10 to the minus 7. This is not a perfect component, a perfect digital component. Each time there is a transition in the input signal, you have a transition in the output signal. And you have a current that crosses both transistors and what we call dynamic current, the current to charge and discharge a capacitance here. If the sweep is very, very slow, oh, this current will not be important. But if it's a fast variation here, if there's a fast variation, this capacitor should be charged and discharged and discharged. And this dissipates power in the transistors. This is what we call the dynamic power dissipation, which is associated with transitions. And it's power associated with the charging and discharging of capacitors. This is one of the most important sources of losses in transition. And this power, dynamic power, is proportional to VDD squared. Okay, this is one of the main reasons to devise technologies that can be supplied by low voltages. Okay, current technologies, most or many of them, are supplied by 1.2 volts. At the very beginning, CMOS was supplied by 5 volts. So you have this proportional to 5 squared. Now, if you have 1 squared, 25 times less than 5 squared. Okay, so this is an important source of losses. Let's make a 10-minute break.
Fui a sacar mi pasito de temprano.
Ah, ya, ¿entendieron bien?
Sí, realmente
Va a durar más tiempo, pero bien, ¿qué han sacado? Ah, pero el
siempre
está bien, mejor. Preferente. No, y 10 años ya está bien. Si había aumentado.
Ah, é 6 horas só.
Depois tem aula, até as 9
Tá bom, boa sorte, então. Tá bom? Sim, eu já falei com o Gustavo, ele veio aqui embaixo.
Deixa.
Sim, o Walter falou. Tu também tens que deixar, não?
Não, não. Todos nós.
É 5? Ah, todos? Ah, porque vem uma turma. Eu acho que vamos concluir.
E depois temos.
Ah, eu achei que.
E esse eu sei que nós
Sim, vai ser aqui, eu já sei. Tá, não tem problema sair. Tem problema.
Activo. Está un año activo, 5 y 10 ya debe estar activado, ¿no? Bajo porque está en clase todavía. No, entonces el activo puede pasar.
Sí, quería decir que el profesor.
Question. Yes. Yes. Yes.
Example, this one, the differential design and I see. And the direct signal. How we can solve the direction of both transistor or differential. To match, for example, their parameters.
Okay, you are talking about the differential pair, right?
The parameters for the temperature, absolute temperature.
Okay.
Because of the parameter.
Okay. Say that you have just one transistor here and the other there.
Yeah.
Okay. And one and two. Oh. For very, I would say, for very low
Mañana se
power dissipation circuits, assume that the temperature will be yes.
Pero ya vengo con mis
And you will not have
eventos.
to care about the temperature difference. But
Por eventos.
if, say, you have some source of heat, then this here, thermal, isothermal curves temperatures. So here is, let's put something. Then you would have a temperature gradient from here. Then what do? You generally, instead of putting one transistor here and there, you split the transistor. Okay. Say M1. Just like a simple example. In this case, if the isotope is here. So you connect this one to this one, this one to this one. So you split these two transistors into parallel associated transistors. Then you would have something like this. Sometimes You split each transistor in four. What you need is what we call a centroid structure. You have a common center of the transistor. This is not so simple in some situations, but you try to do this. This is what we call centroid. So you have a, say, a geometrical centroid or a center of mass, but you have to split the transistor. But in general, you do this because you want to matching. Sometimes you have because the process, the machine that builds the process, there are several steps. 100 steps to build this transistor. Sometimes the machine doesn't operate equally for both. Another is that you should keep these devices very close to each other. Okay. And even in those cases, you have some difference. Say this transistor, let's say that a given characteristic depends on the number of dopant atoms. But here you have 49 atoms. You have some variation, 51 here, 50 here, and 48 here. Now, you see that the characteristic depends on the number of atoms. And here you have an average number which is different from the average number. So if you increase the area, the matching, the average number becomes more close to each other. When you have small areas, this could happen. Okay, it's like making the average in any environment. Say, if you have taken 10 students and you calculate the average height, you have some number. If you take 1,000. If it's a greater population, you have more accurate value of the average. And this is what happens here, right? More area, more accuracy. More area. In general, okay, this is one of the main rules in analog integrated circuits. One of the main rules, more area. So this process, because this is silicon. Okay, if you increase the area, the cost of silicon.
There's a trade-off.
There is a trade-off. Oh, I have to balance what can I afford this area, is that acceptable for my design? Because sometimes I have a limitation of area, say, oh, I cannot have an area greater than 10 by 10 millimeters, so I cannot increase the area as much as I can. Have to limit. More area, less blocks, less circuits. So there is a trade-off, and you should know how to balance this trade-off, right? Area versus accuracy. And sometimes you also spend current, you spend power. This is another problem, okay? Maybe not in this case, it depends on your design. You are the engineer who is creating a design, so you can balance. So it's not simple. In fact, for this area, that's the reason why there are so few IC designer, integrated circuit design, because it's an area there, I would say, very difficult. But many designers, they try to design using just EDA tools. But the EDA tools for analog designers are not very intelligent. We don't have, maybe in 1 or 2 years with the artificial intelligence, maybe you have good designs through the artificial intelligence means in ways, or software, or what.
So these machines are more useful. Yeah, so these machines.
See, digital design, they have a lot of tools that you have a lot of circuits which are ready for. But what do you want? Why? Just to go to the library. It's not like analog circuit, which is much more difficult because we design at the transistor level. In the digital level, nowadays you design at the algorithmic level or at the language level. You use language such as VHDL. So you describe the device you want or the function that you want, not the device. So you have software that will give you the circuit. You write some lines of codes and then you have a circuit in silicon, given technology. I don't know. I know that most of my students are moving to Europe or to the USA because there are lots of positions for analog, even for digital. Okay. And I see there is lots of positions open. I don't know what will happen in the future with artificial intelligence. But this is it's true for every profession, not only for engineers. Okay. Okay. The first stop, the next stop of my presentation is about small signal analysis. And for small signal analysis, I will start with the small signal transconductance. Okay. Okay. The MOSFET has 4 terminals. So you have 4 transconductors, each one associated with each terminal. So let's define the 4 transconductors. The first one is GMG, is the transconductance associated with the gate. What's this transconductance? It represents the derivative of the drain current with respect to the voltage. This is like the GM of the bipolar. GM of the bipolar, what it is? The derivative of the collector current with respect to VB, right? But here we define the transconductance with respect with each terminal, not with a voltage difference, right? So GMG is the derivative of ID with EG. GMS, there is a minus here. The reason for that is that this transconductance, okay, is the drain current decreases with the increase of the source voltage. That's the reason why there is a minus. A GMS will be positive. If the drain current decreases with the source voltage, then GMS is positive. GMD, the derivative of ID with respect to the drain voltage. GMB, derivative of ID with respect to the bulk voltage. Okay? So, you know that to calculate a small difference in the drain current due to small differences in the gate, in the terminal voltage, I can write this expression as the variation due to VG plus the variation due to Vs. Look the sign here because I have another sign there, another minus sign, plus the derivative with respect to the drain voltage times the drain voltage plus GMB times delta VB. Huh? What happens if you make all the variations equal? Suppose that you have the MOSFET, you have constant voltage at each node. Now you move all the voltage by the same amount, right? What happens to the current? You move all the voltage by the same amount. What's the result of the current variation? Should be zero. Because you know that the current, let's say, depends on the voltage difference, such in a resistor, right? So if delta VG, delta VS, delta VD, delta VP are equal, then delta ID equals zero. The conclusion is that, well, delta ID is GMG minus GMS plus GMD plus GMB times delta would be zero. Then the conclusion is that the sum of all transconductance equals zero. So in general, you need only 3 transconductance to define the variations in the drain current. Okay. Now let's calculate GMS of a long channel device. This is simple for us. What's ID? ID is a combination IF minus IR, right? What's IF? IF is the current component which depends on the gate voltage and on the source voltage. And IR, the current component which depends on the gate voltage and the drain voltage. Therefore, I can remove IR from here because it doesn't depend on the source voltage, right? Then I can write this expression in terms of IF. Okay, what's IS? IF, I can. This case of IF equals IS times IF, right? Okay. IS is not a function of the source voltage. Then I can remove this from the derivative. And I can say that this derivative equals IS times the derivative of small if over s. Now I go back to the expressions that I know. I won't derive once again, and we can conclude that the derivative equals minus mu W over L QIS, which is the inversion charge density at the source. Okay? I can also write this expression in terms of the inversion charge, the inversion current, the forward current, sorry. Because I know the relationship between charges and voltages. So instead of writing that QIS, I can use this value of IF and substitute here in terms of IF. It will appear later, the dependence of GMS on IF. Let's keep it as is in this form right now, okay? But since I know the relationship between charges and currents, I can write this expression in terms of inversion level at the source. The same for GMD. This is for a long channel device, okay? After that, I'm going to change this a bit for the saturation transconductance. What is GMG? Okay, this is how I can write ID. Then DID, DVG can be written as the derivative of all this term here. But for practical purposes, this is not exact, but I'm going to assume that IS is a, say, light function of VG. And I'm going to neglect the variation of IS with VG. Then I can write this expression as okay. In practice, I can rewrite this expression in terms of GMS and GMD. And then I can use these two previous expressions, okay? And okay, this is simple algebra. And finally, the last transconductance is transconductance to the bulk. I can use this sum here, which is 0, and can derive this expression. Okay? What if n equals 1? What would happen here? MB would be equal to 2. What's the meaning of this? If n equals 1 means that we don't have depletion capacitance. The depletion layer, the ionic layer, would be 0 or it doesn't change. In fact, it doesn't change. The derivative is 0. Okay, this is the interpretation of this, one of the interpretations of this equation. Okay, so we have this set of equations that characterize the transconductances for a long channel device. This is not valid for a short channel device. Okay? I can give another set of expressions for GMS, GMD, and GMD using the relationship between charges and currents. I use this. Note that QS minus n C out phi t. Then I can use this expression, this one, to calculate the transconductance in terms of the inversion level. The source transconductance is associated with the inversion level at the source. And the drain transconductance is associated with the reverse current or the inversion level at the drain. Okay. And And we can replace IS in terms of mobility, etc. And the G given by this expression right here. There is an important figure of merit for transistor, which is called inverse conductance to current ratio. This relationship is dependent on both the inversion level at the source and the inversion level at the drain. Okay? What happens when VDS is very small? When VDS is very small, you see that the channel is uniform. So if you move the voltage at the drain or at the source, they have the same effect, right? So I can place this expression with this one here. Okay. What happens when the device operates in saturation? Saturation means IR is much smaller. And we can replace this term here by 1, and you have a simplified expression in saturation for the case IF much higher than IR. Okay. Okay, this is this schematic circuit of the low frequency model of the MOSFET. We have 4 current sources. Each one is controlled by a terminal voltage. Okay, and look here, due to the negative sign that you define this GMS, this current source points towards the drain instead of the source. 3 other current sources point to the source. Okay, this is valid for both NMOS and PMOS devices because this is a variation model. It's not a DC model. This is a model for variation. Okay. I suppose that we have to read. Okay, so see you tomorrow.
Professor, one question. Measure did you consider a short channel less than 100 nanometers? So,
Short channel.
yeah, less than 100 nanometers?
This model. Or
Yeah, because you have shown the equation for long channel.
Okay, this is for a long channel, but long channel doesn't mean that it's 100 or 200. It depends on the technology. Say, if you are talking about 180 technology, maybe a long channel would be 1 micron, maybe 5, 6 times more. It's not an absolute. In fact, a long channel doesn't exist. This is a fictional picture that we use to introduce the model. And after that, we must introduce short channel effects. All transistors have short channel effects, but depending on the problem that you are dealing with, you use or you don't use this short channel, okay, parameter. Okay, but up to now, this is for a hypothetical long channel device. Okay, that doesn't have
So
long
if I
channel,
want to
short channel
avoid
effects.
that space, so I choose the first channel or the second. Well, the first model or the second.
You have to choose the model depending on the problem that you are dealing with. For example, if you want to calculate the absolute value of the current, it doesn't matter too much if you assume that the current has saturation or not, if the slope is small. So in general, we use long channel models to calculate the DC current. But of course, you cannot do it for calculation of a voltage gain, because you need the slope of the characteristic of ID versus VD. So that's, you need some, I would say, experience to deal with each problem. So you have to get some feelings about the problem that you have to solve. Okay? Any other question? No?
Muy bien, muchas gracias. Ahora vamos al 103, a la conferencia. Tenemos unos 20 minutos de break.
Okay.
Y en el 103, exactamente debajo, tenemos la conferencia. La otra cosa que quería decirles es que tanto el material como la grabación de las clases van a estar disponibles para ustedes. Obviamente con el permiso del profesor. Sí, se está grabando todo esto, sé que actualmente pues ustedes tienen mi correo, a mí me van a facilitar el enlace seguramente para que puedan bajarse la